Hello, my name is Muhammad Alif Hanif bin Rosmat and my metric number is DE20087. Today I'm going to present to you the introduction of my group project. Okay, for the project background, in this project, our group will suggest a design of power system network for industrial based on the industrial loadings. The suggested design is particularly meet with requirements such as simple structure, cost-effective, reliable, and the most important aspect is the sustainability of the network. Based on the provided industrial loadings, the structure of the power system network is designed as simple as possible, but at the same time, all equipment are ensured to able to operate smoothly and function properly to supply the power to the industrial loads. Besides, the cost-effective aspect has also been considered during the design process to limit cost of installation. The rating of the transformer are calculated to prevent oversizing that may increase the cost. Finally, the design power system network is also ensured to be sustainable and reliable. Expansion option is considered during the planning process to prevent all of the equipment need to be replaced if the expansion of the power system is needed. Okay, during completing this project, there are several technical problems that need to be considered during the planning and designing process of the power system network. These technical problems are crucial because it may affect the sustainability of the power system in the future if it is neglected during the early process. Okay, for the first technical problem is what is the design of power system network to support all the industrial loadings. The second one is what is the variable that need to be considered to choose the sustainable equipment in the design network. And the last one is how to design a sustainable network design for the industrial power system. Okay, for the objective of the project, there are three objectives that need to be accomplished in this project, which are to calculate the energy consumption of the given industrial loads, which included the current, voltage, and power of the load, to design a sustainable power system network with suitable rating of transformer and cable with consideration of future expansion options. And the last one is to analyze the design power system network where when there are 60% load expansion situation and provide reasonable solution. Okay, that's all from me. Thank you.
Assalamualaikum. My name is Abdul Razak and I will continue for the overview of project planning. So this is our flowchart. So first is we do the single line diagram. From that we can calculate the load demand calculation for all the load for division 1, 2 and 3. Then the next step is calculate the transformer sizing. So after that we need to check either it meet the transformer criteria or not. If not, we have to increase the transformer rating. Then here we have the calculate to cable sizing. So as we know, cable sizing has 3 criteria, which is criteria 1, criteria 2, criteria 3. For the criteria 1 is the short circuit current withstand capacity, and then criteria 2 is continuous current capacity, and then the last one for criteria 3 is starting and running voltage drop. So we need to calculate for each criteria and check either it meet the requirement or not. If not, we need to increase again the cable size. So if yes, we can do the next step for 60% load expansion, and then we can analyze all the criteria for the cable and the transformer. Finally, we can propose the solution. So for the next one is the description of proposed industrial loading. So from the given data, we have 3 divisions, which is the division 1, division 2 and division 3, which has individual load. So we can assume each load either it is a continuous or a standby. Here we can see an example, which is the induction motor 1 is a continuous, meanwhile the induction motor 2 is on standby. So with the given rated voltage, motor HP, efficiency and power factor, finally we can calculate the apparent power for each of the load. So here we can see that for division 3 there are 2 different rated voltage for the load. Thus the 1230 horsepower synchronous motor as a continuous load will be operating at 6.6 kV. And then for the other load, which is the 415 volt, a step down distribution transformer will be needed. So the last one is the description of proposed industrial network design. So in this project, the single line diagram which we designed at first to picture the overall network connection. So the main idea is to design the single line diagram to have a main distribution transformer to step down the voltage level from the grid network. So after each division will be proposed with distribution transformer to the supply to the load in each division. So controlling equipment such as switchgear, switchboard or distribution board will be included between the connection of the transformer and the load. So the transformer size will be included in the single line diagram, and those information will be obtained after the calculation is performed. So we can say that by completing the single line diagram, it will give us a better picture of the design network and state out the detail of the equipment in the single line diagram. So I think that's all from me. Thank you.
Hello, my name is Tim Morgan, son of Levi. My merit number is DE200101. So today I will present about 2.4, which is a description of transformer and cable sizing works, and then followed by description of future expansion options, and also environment and sustainability design issues. So for the description of transformer and cable sizing works, we need to refer the single line diagram. The size and rating of the transformer will be determined based on its voltage level, rating, and impedance for every selected transformer. So basically, we need to refer to the single line diagram to find the, first of all, we need to find the rated current of transformer. So this is the formula, rated current of transformer, which is equals to rating divided by Z3 times by secondary voltage, and then followed by the short circuit apparent power of the transformer, which is the second formula, which is equals to Z3 times by secondary voltage times by rated current of transformer, divided by percentage of impedance. And then the rated current of transformer will be used compared with the full load current of the load during the transformer sizing. So after that, we need to find the voltage drop. So why we need to find the voltage drop is because of we need to make sure the voltage drop at the secondary is lower than 10% using this formula. So after finding the voltage drop, we need to find the we need to move on to the cable sizing. So for the cable sizing, we need to use criteria 1, which is the short circuit current withstand capacity of the cable using the formula given, which is equals to short circuit current times by Z divided by K. And then after the calculation of the criteria 1, we need to move to the why we need to find the criteria 1, because in cable sizing process it's important to ensure the cable can withstand the short circuit current before the protection equipment cut out the supply source. So after that, we need to find the criteria 2, which is the continuous current carrying capacity. So to find that, why we need to find that? Because to ensure that the minimum cross section of the cable can carry the required load current continuously at the designed ambient temperature and laying conditions. So this is the following criteria 2 equations: K equals to K1 times by K2 times by K3 and K4, and followed by other Ks. So after that, we need to find the criteria 3, which is the starting and running voltage drop in cable. So why we need to find that? Because it's to ensure the cross-sectional area of the cable is sufficient to keep the voltage drop within the specified limit, so that the equipment which is being supplied power through the cable gets at least minimum required voltage at its power supply input terminal during both starting and running conditions. So after that, we need to find the we need to calculate the voltage drop in power system to determine whether or not the voltage will remain with the acceptable limits. So this is basically the formula of voltage drop, and then we move to the description of the future expansion options. So in the future, it might be the business growth is too good, and then because of that, we need to expanded the industrial network because the business is growing very good. So the 60% of the existing load is the total increment, and three will be, and there will be two more new division is going to be included into the existing network. So we need to add up division 4 and division 5 for the upcoming upcoming future industrial network. So this is the load duty, rated voltage, motor HP, efficiency, power factor, apparent power. So this is the things that we need to be included in the upcoming calculation. So for the division 4, we have induction motor 5, 6, and 7, followed by division 5, which is induction motor 8, 9, 10. So those are the 60% of expansion load that will be included in the existing power system network. And then there are a total of 3,444.48 kilo apparent power, reactive power of a new load will be added into the industrial power system. So the new design of the network will be need to be designed to make the power system able to sustain the new load and not affect the existing load. So that means we need to create the new line diagram with the new transformer included. And then there will be environmental and sustainability issues, design issues. So for the example, we have one main distribution transformer. This is the one of the issues, which is a one main distribution transformer only. Meaning, if the transformer is facing a sudden failure or in undergoing maintenance, there will be no other transformers to back up the system as a main distribution transformer. So all the loads need to be shut down, which can cause great problem for the industrial productivity. So followed by another issues, which is a oil type transformer. We are using oil type transformer, which has the negative side where the oil is subjected to negative influence such as temperature, oxygen, and sunlight, which will cause aging of the oil, thus degrading the process, the performance to the point it needs to be changed. So basically, that is the what we call environment accessibility design issues. So that's it for me. Thank you.
Hi, my name is Tommy Lim and my metric number is DE200108. So I will explain about the project outcome and discussion. So I will start with load demand estimation. So this is the table of calculation for load demand. So this is the load in each division, and the load duty is state here by using C or S. So the utilization factor also is assumed based on this node, and the power will be obtained by simply based on the detail of the load. So the apparent power here is obtained by using this formula, and simply multiply the apparent power with the utilization factor, we'll get SKU, which is also apparent power, after multiply it with KU. So this is the diversity factor for in each division based on the distribution component. So in here we will have this MCC connecting three different type of load. So the KS will be 0.9, and sum out all these SKU in division 1 and multiply it with 0.9, we will get a new apparent power here. So the same process is performed in division 2 and division 3. So at last, for the main switchgear, and we will sum out this value, the apparent power, the last apparent power in each division, and multiply it with 0.9 and obtain the value of 3400 something in the last column. So for the total maximum demand, we will also consider the 25% of future expansion, and this is the formula we use. So by plug in all the value, we will obtain the final value, which is 4,300 kVA. So using this value and compare it to the supply scheme provided by TMB, we obtain that the supply voltage is equal to 22 kilowatt. So next, for the single line diagram, which is also the industrial network design, you can see we will have the T1, which is the main distribution transformer, to step down the voltage level to 11 kilowatt, and the switchgear is used to distribute the supply to each division. So each transformer will have different rating, as we can see here. So MCC, distribution board, and switchboard are used to control and distribute the supply to each load. So next we'll move to the discussion on transformer and cable sizing. So we'll start with cable sizing. So the main idea in cable transformer sizing is to ensure the voltage drop at secondary of the transformer is below 10%. So as you can see here, this is the information we can obtain from the previous calculation and from the load and the transformer rating. So just plug in this value, and to obtain the short circuit apparent power of the transformer, we will apply this formula, and the secondary voltage, the rated current, and the impedance level can be obtained here. So just plug in this value and use this formula to obtain 200 MVA for T1 for the main distribution transformer. And for the voltage drop formula, we will need to use this formula and again plug in all the value obtained into this formula, and lastly we will get the result for voltage drop. So as we can see here, the voltage drop for each transformer is able to maintain under 10%. And the next table is showing the full detail of transformer. Next, we move to the cable sizing. So the criteria one for cable sizing is short circuit current withstand capacity to make sure the cable able to withstand the short circuit current. So here we have fault clearing time for each cable. So here we can see in the next table, the cable one, the cable type, the circuit breaker type, and the fault clearing type just obtained from here. And the short circuit temperature rise constant is based on the type of the cable. So the short circuit current, and to obtain the minimum required cross section area, we will apply this formula. So just plug in all these value into this formula, and this is the cable size we obtain after perform the calculation in criteria 1. So next we will move to the criteria 2, which is continuous current carrying capacity. In criteria 2, it is to ensure that the cable size can continuously carry the current during the load operating time. First, we will state out the cable capacity and state out each duration factor that include in the calculation. So after multiply all of these using this formula, we will get a number of duration factor, and this will be multiplied with the cable capacity and the total run of the cable. So we will get this value, which is current carrying capacity, also known as I3. So the I3 will be compared with I1, which is full load current, and we will need to make sure I3 is greater than I1. So as we can see here, this is the final chosen size in criteria 2, and we can observe that the cable 2 and the size of cable 2 and cable 3 has increased compared to the criteria 1. And next we will move to criteria 3 to determine whether the cable size need to be increased or not. So for criteria 2, it is starting and running voltage drop in cable. So this is the voltage, this is the load current, cable length, resistance and reactance of the cable is different based on cable size. So we will refer to this size. And for the cos theta, sin theta, it will be separate into two, which is during starting and running, and this is the number of cable runs. And by using this formula, plug in all the value here into this formula, and we will obtain the voltage drop of each cable during starting and running. So the objective of criteria 3 is to make sure the percentage voltage drop of in each cable is less than 3%. So the result of cable selection will be same as in the criteria 2. So this cable size is suitable to be used, and this is the final result for the cable selection. And all cable material are coupled with XLP insulation. So that's all for my presentation. I will pass it for the others member to continue.
Hello, my name is Muhammad Amiruddin Masudizam. My material number is DE200123. I will present about the outcome of the new design. So basically, the outcome of the new design is the addition of our division 4 and 5 as required by the assignment. So for the division 4, we will add 3 induction motor, which is induction motor 5, 6 and 7. And for division 5, we will add also 3 induction motor, which is induction motor 8, 9 and 10. So after we total all the division, which is division 1, 2, 3 and 4 and 5, we will get a maximum demand, which is 1163.75 kVA. So based on the table above, when the extra 60% load is added into the network, there are 3 new transformers need to be included in the new single line diagram. So for the division 4, the rating should be 11 kV down to 3.3 kV, 6 MVA with 5% of impedance, while for division 5 is from 11 kV down to 415 volt and 0.5 MVA with 3% of impedance. So the size of the transformer will be able to sustain the load and match the criteria of the transformer sizing. The criteria is to keep the transformer secondary voltage drop lower than 10%. So as the main distribution transformer, the same rating of transformer will be added parallelly with the existing transformer. So we choose this design because when the transformer is connected in parallel, the supply voltage will remain at 11 kV, but the output current can be increased. So this is our single line diagram for our network. So for the environment and sustainability, so we propose a solution. So for the solution, if the only main distribution is under maintenance or failure to operate, the secondary or backup component need to be installed to act as a standby supply. So the circuit breaker on the low voltage side must connected with the high interlock to prevent the transformer from operating in parallel. So it was to provide a switching, isolation and protection device on the end riser of the individual transformer. Besides, for the load that require continuity power supply, it also a wise step to connect an industrial generator to the load. Thus, when the transformer failure occurs, the load will gain supply from the generator until the transformer is fixed. In addition, as the oil used in transformer is different with normal fuel oil, it can be treated and reused again. But as a product that can be reused, to implement this approach, use transformer oil reclamation technology is needed. Such technology allows to restore the dielectric liquid performance, extending their service life. So another approach to mitigate the risk of leak or catching fire is install the extensive shielding and concrete posts to contain spillage. The transformer for a sustainable wool by Ryan Lake using biodegradable ester fluid also reduce the need for extension surrounding infrastructure where ester fluid not only lower the risk of fire but also eliminate the environmental risk for possible spillage. Furthermore, inspection and maintenance will need to be done occasionally to detect any problem regarding the transformer. If the leakage is detected, the maintenance need to be done instantly before it can be continued operating.
Assalamualaikum and selamat sejahtera to Doctor. So my name is Rashid bin Rasul. I will present about our conclusion of this project. So as we know, in industrial power system, it is important to keep the industrial gain stable and sustainable supply to operate efficiently. Therefore, the planning design system network is crucial during the early process. It is because a good design will prevent charge to be implemented after network being used for few years. As we know, charge in industrial will cost them money and time. If the production need to be cut due to maintenance, some machine and equipment cannot be used. So for this project, we learn how to plan and design reliable power system network based on given load. The planning and design industrial transformer cable sizing to determine suitable cable to be used, and calculation made based on the formula and comply the basic criteria for each equipment. During the process, future expansion option is considered with the concern to minimize charge need to be done when there are additional load in future. Furthermore, the detailed analysis for the design is also have been carried out to identify the weakness of the design so that the proper solution can be provided for the design. For the instance, for oil type transformer proposed in the design, inspection need to be done from time to time to prevent leakage, and maintenance also need to be done when oil dielectric strength has decreased to a certain level. So for the 4.2 weakness of the proposed design, in this design there is a weakness which is design its proposed system mainly equipped main distribution transformer and no backup supply in the power system. And if any breakdown happen, the load must be shut down until the maintenance done. This will be issued to the output of the industrial itself. So all the load such generator, induction motor, kit motor during the maintenance period. Beside all of the proposed transformer is oil type. We know oil type is cheaper than dry type, but the downside of this transformer is require maintenance from time to time. Thus production may need to be shut down during the maintenance. It will also cause a minor loss to industry. So that's all from me. Thank you and Assalamualaikum.